the next speaker that will be talking about the COVID-19 simulator, and that team is Zongliang Yue, Eric Zhang, Diane, and Rubio Pique.
Hello, everyone. I'm Zongliang Yue, the team leader of the team number 6 from the Informatics Institute in UAB. And our project title is a network-based SEIDR model named as N-SEIDR. It's a new modified epidemic model in simulating the outbreak of COVID-19. In the introduction, I will introduce the overview of this COVID-19 severity and traditional models in use, like SEIR, and also our new network-based SEIDR model, N-SEIDR. The novelty of the N-SEIDR comes from the 3 aspects. We have bring in the social network. Also, we introduce new states and parameters, as well as new parameters in optimization. In the result, we highlight that our new model have a high accuracy, can capture curve changes and their major driver factors, and project the transmission dynamics. As we know that is COVID-19 has a huge impact in public health. Unfortunately, we have no pharmaceutical treatment available. The only efficient way to prevent the potential spread through interventions such as contact tracing, quarantine, and social distancing. Therefore, there's an urgent need for epidemic model to predict the cases and provide guidance of public health, such as answer the question how initial pandemic wave unfolds, the possibility of the resurgences, and when it will be, and how many ICU beds will be in need in the future. The traditional SEIR model has these 4 compartments: susceptible, exposed, infectious, and recovered. There's a set parameter to control the transmission rate between these states. Like the recent published paper in Science, they have applied this naive SEIR model. Notice this is a static parameter, which means once this parameter has been determined in the beginning, it will be fixed during the simulation. And there's no social network information in this model. Another paper coming from a simulation in Singapore, they have an improved version, have a social network used, quarantine strategy. Also, they report that combined of the 3 different quarantine strategy will have a good surprise of the number of infections, but still they are using the naive SEIR model. Therefore, we are introducing the N-SEIDR, which have the 5 states. We have additional states, disease states, because with a large number of diseases cases in this particular COVID-19, which could not be ignored. And also we have this novel subcategory of this infected state, ICU, inpatient, outpatient. By introducing these new states, we can possibly predict hospital capacity in need in the future. Correspondingly, to that new state, we have these novel parameters. Omega is the rate of an initial infected transfer to 3 infected substates. Lambda, the rate of death due to infected. Gamma, the rate of infected state to recovered state. CFR, case fatality rate. So by using these refined parameters, we can properly infer the CFR, and this CFR allowed us to monitor the virus toxicity, and this has been put into our ordinary differential equation model. In our new model, we have bring in this social networking. In the traditional SEIR model, it's more like a state-level quarantine, which assume all the individuals in this population are fully connected. But we know that this is not a real case. Therefore, we construct the social network in population follows the power law distribution, which there's a few number of hub nodes and a lot of the peripheral nodes. And the network will effect the case increasing rate that a family level quarantines has a smallest case increasing rate that's simulated in our SEIDR model. We also have introduced a new parameter theta in this network to control the intergroup contact rate. So for example, this have a case of the two family with numbers 4 and 3 contact here. And this, if we accept this is a contact, we will use this new beta join to do an update of the exports cases in the population. Compared to the no contact scenario, the beta joint has a larger exposed case delta changes. In the simulation, we bring in two novel simulation parameters. One is window size, the other is E0. Window size allow parameter change with windows. The default is 14 days per window. E0 is inferred initial exposed cases. Since there's no official report for potential exposed number on day 0 simulation, therefore this parameter allows model to match the real case well in the beginning. For the parameter optimization, we use a mean square error as an error function. For the parameter optimization step by step, we have used this SODT, sequential optimization using decision tree, which we have a custom range of the parameters. And this SODT can go through possible parameters in different directions, whether to increase or decrease the parameters through the decision tree. And this decision tree helps to minimize the cost of the evaluation. In the result, like we have simulated a case in the Jefferson County, we use the community as a quarantine level, and every side of the community is 3,000. The first day of the infected case reported in Jefferson County, Alabama, is on March 13th. We have two types of line here. The dashed line is the in real data cleaned from the Johns Hopkins data source, and the solid line is the curve we predicted in a model. In the traditional SEIR model, we can see the performance is very poor. There are only a cross point along the way. But in our model, we can see a perfect match between the solid line and dashed line, which in the end, we have tremendously reduced the mean square error and have the 50 times better performance compared to the baseline model. Next, we are going to seek the driver parameters of the curve fluctuation. Like we have that well-fitted curve. So what parameters really drive these curve changes? We found that the two parameters have been used as the key factors in the confirmed case. Beta is the successful infected contact result in a new exposure. Theta is the group-to-group contact rate. And we observe that in the beginning, it will have a large number due to there's no distancing policy applied. But afterwards, it increased. For the thesis curve simulation, we found the case fatality rate in ICU is the key factor. And therefore, we also have found a average case fatality rate in ICU is around 50%, which matches to the doctor's reports. To provide you a better understanding of this N-SEIDR, we show the confirmed cases propagation in the community network of this Jefferson County, step by step. Remember, these three parameters have an influence in this confirmed case propagation. And And therefore, we observe that the first window have the largest beta, theta, and sigma. Therefore, we see that immediately as the next window begin, we have 3 community infected add-on. And from window to another window, we have because the parameter threat is low, so there's a few community have been added on from the bi-week window. And finally, to the date a few days ago. Although we have this great simulation in Jefferson County, can we also find some insights of other counties, such as we choose 3 counties in comparison: Jefferson County, New York City, Hennepin County, where Minneapolis is located. And we see the overall trend of these parameters are decreasing and have a fluctuation. Observe that the day, March 25th is when the protests start. Therefore, we observe that the SEIDR have a different kind of scale time of increasing. Afterwards, we also can extract the possible policy parameter side, like no distancing is in the window 1, and moderate distancing and strict distancing, and further apply to the projection. Afterwards, in this inside the project,
sorry, we had to move the questions. We're running a little bit late. Sorry about that.
Okay.
You know what? I know it's probably your answer. Address this in your slides, but kind of what are next steps? What will you be doing? What kind of challenges will you be addressing next?
The next, we will going to say the network structure we are inferred. We propose to extend it to a real social network. Like it's likely to be a mixture network model consists of family and community together. And also, we need to collect more data to infer the parameter ranges to improve accuracy, since there's multi-local minimums have the same equivalent to drive the curve shapes, and we may need to overcome the local minimum pitfalls.
Where does the data come from in the snowflake graph? Is that from the simulation and real data, or that's just a kind of?
Yes, so back to the slides here, this data is coming from Johns Hopkins, and it's updated daily. So we can automatically pull up this data and update our system by daily.
I think I'm referring to the snowflake, the one that it looks like a social networking kind of graph.
Yeah, 2 pages back. Further.
The social network here. Sorry.
Yeah.
Oh yeah, those.
Is that the
Where do
model
you
or
get
is
the
that
data
the
for
real
those?
training data?
Yeah. This network is simulated because this is in our model, and because this is driven by simulation of the real data curve here. So it has the best fit curve, and we want to simulate a network to match to this real case.
Thanks. I have to move on to the next.
Okay.
Topic.
Also, yeah, thank you for
Sorry.
your prize.
Yeah.